So now we are going to talk about train error versus test error. So let's see. So now consider a new point x comma y which has not been seen during training. Right? So what I mean by that this is where I was kind of ending in the last video. So you are given some training data and based on that you have estimated f hat x, right? And now consider some new points, right? And one such point x comma y which was not there in the training data, right? And now you want to see what is the error that this model makes on this unseen point. Why unseen? Because it was not seen during training, right? So that's what the setup is. So if you use the model f hat x to predict the value of y, then the mean square error is given by this quantity, right? So this is the expected error. And why do we have an expected? Expectation means like roughly average or mean. So what is it that we are taking the average on? So again the situation was I had certain training data and then I had certain test data, and this test data had many x comma y pairs. So the average error over all these x comma y pairs, right? That's what this expectation stands for. I want to take this mean error over all the x comma y pairs, and potentially there could be like a large number of test points, right? So if I have built an image classifier, there's an infinite set of, practically infinite or large number of images that I could feed it at test time, right, which it has not seen at training time, right? So every day I don't know how many images get uploaded on Instagram, Facebook, etc. So if you have trained a model using all the images that were there till today, in another 1 week some million other images will get generated, and now all of these images are not seen by the model during training. And now all of this, if you feed it to this model, you are interested in knowing what your expected error would be, right, which means the average error across all these unseen images that you have, right, and average you can represent as expectation, right. So this is the quantity that you are interested in, and if you can show that this quantity is actually equal to bias square plus variance plus sigma square, and it's not hard to see how you will go from here to there, because this is f of x, right, and we had seen that in the formula of bias you had e of f hat of x minus f of x, and similarly in the formula of variance you had e of f hat of x minus e of f of x the whole square, the expectation of that, right. So these terms are there in the bias formula, these terms are there here also, and there is a square here. So if you open up the square by applying the formula for a minus b the whole square and then do some rearrangement of terms, you will end up with this quantity, right, because this bias square is again going to be some square of this, the variance again has the terms that you have on the left hand side. So if you rearrange all of this, you will get this, and there is of course a formal derivation of this available online, which we have linked here. So if you want to see the full derivation, you can see this, but what you can show is that the expected error on unseen data is actually dependent on the bias and the variance also. So if you have a model which has a high bias like the simple model, then your expected error on the test set is going to be high. If you have a model which has a high variance like this high degree polynomial that you had, then again your error on the test set is going to be high. So what you need for this quantity to be small, you need the bias also to be small and the variance also to be small, and the intuition that we just developed is that these are contradictory, right, you cannot have both, you will either have a high bias and low variance, or you will have a low bias and high variance. So somewhere in middle you have to find the sweet spot where you have medium bias and medium variance. That would give you the minimum error that you are seeking on the test data, right. So that's the connection between bias, variance and the expected test error or the mean square error that you would have on the test data, right, or the unseen data. Yeah. So this is the situation that we have, right. The parameters of f hat x, all the w's that we had, they are estimated using the training data, because that's all you have, right. But now why are we training the model? Because at test time you will get new images and you want to classify those images. You want to say whether this image contains a bird or a parrot, or does it contain a lion, and so on, right. And that is what you want to do at test time. You are going to work with unseen images, right. Unseen meaning images which are not seen at training time, right. So now this gives rise to the following two quantities, right. One is the training error, right, which is the error that you get on the training data. So what does that mean? I think we will define that quantity formally soon. And the other is the test error, which is the error that you get on the test data, right. And you would ideally want both to be 0. You want the training error to also be 0. That means once I have trained the model, at least for the training data, it should be able to predict everything perfectly, right, give me close to 0. And then of course on the test data also I want it to be 0, right. So typically what happens is these errors exhibit the following behavior, that if you have a high model complexity, right, and in our case we saw this degree 25 polynomial, if you had increased it further, it would have almost perfectly fit the training data. That means my training error would have gone 0 as my model complexity increased, right. But what would happen is the test error would behave like this, right. If my model is not complex like the linear model that I had, which is the one extreme, then my test error is going to be high, as the red curve is high there, right. But if my model is very complex, then also my test error is going to be high for reasons that I mentioned earlier, because now I have trained the model to completely overfit on one training data that I had seen, and now if I have another points which are not similar to this, or which are not which were not seen during training, then I don't know whether it will be able to perform well, because its entire universe was restricted to these points and it did like everything that it could to fit those points properly, and in that effort it might have now missed considering the other points which are unseen, right, and for those points it will make a high error, right. So this is typically the behavior, that the training error will keep decreasing as the model complexity increasing. The test error will decrease up to a certain point, but if you make the model extremely complex, it is going to overfit on the training data and make severe errors on the test data, right. So what you are looking for is the sweet spot somewhere in the center, right. And on the left hand side you have high bias models like the simple models, which give you very high error both on the training data as well as test data, right, because the simple line model, even on the training data, it was giving us a high error, it was nowhere close to the true sinusoidal function. And on the right hand side you have the high variance models, which give a low error on the training data but still give you a high error on the test data, right, and you are looking for this sweet spot somewhere in the middle where you have a good trade off and you have the ideal model complexity, right. So now let us formally define the train error and the test error, right. So let there be n training points and m test points, right. So these are the n training points that were given to you. Then you can define the training error as this, right, which is known to you. So over all the n points I am going to take the average mean square error, right. So average square error or the mean square error, that is what I am going to do, and this is for the n training points. And then for the m test points, which is n plus 1 to n plus 1 m points, I can similarly define the test error, the average test error, right. So this is already known to you intuitively, I have just formally defined it. Yeah, so as the model complexity increases, the train error becomes overly optimistic, right, because you saw that the blue curve was showing you, oh, the training error is 0, and you would think, okay, perfectly, I have found the perfect relationship between y and x, but that is only for this training data, right, and as soon as you test it on the test data, you will find the error is high. And so what you actually want is that the validation error should be low, right. So the true picture of whether your f hat is really good comes from the validation data or the test data and not from the training data, right. You want the test error to be small, that means the error on unknown points to be small. Driving the error to 0 on the known points is easy, you can just keep increasing the model complexity and it will go to 0, right. But what you want is to keep track of that sweet spot, and to keep track of that sweet spot you need the test error, because the moment the test error increases you need to stop. You say, I do not want more complexity than this because my test error is increasing, right. Now whatever intuition we have developed so far, we will try to convert this into mathematical formulation, and then we will try to make a case for regularization, okay. So I will end this video here.